Welcome to this third part of Pandas training. In this part, we'll talk about hierarchical indexing, and we're going to start with series. Hierarchical indexing enables multiple index levels on an axis. You can have more than one index levels on a single axis. For example, you might have the following series. In this series, it contains 10 randomly generated normal distributed values, and on the first level of index has A, B, and C, and the second level of the indexing has the values 1, 2, 3, which are the labels. We can go ahead and execute this. So as you can see, is a series with two levels of indexing. We have the first index which has A, B, and C, and we have another level, second level, with the labels 1, 2, 3. Now suppose that we wanted to access B. How do we do it? We first do something we call partial indexing. You want to access only one section or one index based on the first index level. So here we can use data, that's our series, and then we do the normal indexing, and inside the square brackets we specify our label for the first indexing. If I execute this, I get everything that is contained in B. So B has all this. So this is what's being selected. We can also do slicing. We can select multiple indexes or values. So in the first level, we start with our start index, and the last one is C. So it's from B to C. So basically we want to access B and C. And that's basically how to do the slicing. To access the series elements based on the first level of indexing. Now, what if we wanted to get some values based on the second index level? So suppose we wanted to get a subset based on the second index level of the second label. So this is how we do it. So the first, if we have a comma, the first part represents the first index, and the second part represents the second index level. So if I execute this, I get A, B, C, D. So basically what's happening here, I'm getting this value for A, for B, and this for C, and this for, so that's why you're getting only one for each. Then there's something else. Because we have hierarchical indexing, we can do something we call series, stack, and unstacking. Basically is converting the hierarchical indexing in series to be rows and columns, or rather two-dimensional. So to achieve that, we can use unstack function to convert them into rows and columns. And this is how. So we've come from our original, which had two levels of indexes or indices, to rows and columns. So here, the second level becomes our column, and the first level becomes our our row indices. And then what if now we wanted to go back from data to, we wanted to go back from this back to our original hierarchical series. So here, because you see, as you can see, data is in series. But if it happens that you stored this maybe into a data 2 and execute and we run that data 2, this is what you get. Now, if you want to go back to this kind of data or hierarchical index series, so this is what we do. We say data2 dot stack. So you see, we went back to our original format. The next thing we are going to look at is hierarchical indexing in data frames. Remember, data frames have two axes, axis 0 and axis 1. or rather rows and columns. Now, suppose we had a data frame that uses numbers from 0 to 11 and has been reshaped to 4 rows and 3 columns and has 2 levels of indexing. First indexing for the rows is A and B, and the second level has the labels 1, 2, and on the columns has 2 levels. Level 1 is the 3 states, and on level 2, for each state, it has green, red, and so basically it's green and red. As follows, you can go ahead and print this out. So here we have Ohio with green and red, and Colorado with green on the columns, and we have on the rows, we have 2 levels, 2 index levels, A, B on the first, and 1, 2 on the second. So we can use either axis to retrieve the values, and we can change the index names as follows. So to change the names of those index, we say index names frame index dot names equal key 1 and key 2. So if I execute this, you see that we have for the index, for these ones, we have key 1, key 2. So basically we've renamed this one as key 1 and key 2. We can also do the same for columns. So here we see that we use columns dot names. So basically you are changing the names of the columns. So we have state and colors. So executing that, so we see we have state is the first level, and the second level has been named as colors. So to access the values here, we can access based on columns or rows. To access based on columns, we use the normal format. So we say frame, and then we pass the first level column name, which is like Ohio. If I execute that, I get the information for Ohio, and Ohio has all these values. So it has green and red. So basically you are selecting everything on that column. And remember that Ohio has 2 columns, green and red. That's why you're getting that. And now, if you wanted to select a row based on the second level of indexing, so we use iloc. We can use iloc or we can use loc. So for example, if we wanted to get for A and B, we get 1, 1. So this is how we do it. So we are getting for, since we are using the location, so we are talking about this first one here, A. We are talking about A. Sorry, not A, but rather B, because it starts counting from 0. So 0, 1. So we get state is Ohio and Colorado, and it's green, red for Ohio, and we're using Colorado. So basically what is happening here is that iloc 1 is taking the first row, the first level A, or so basically it's getting this row. Hope that is clear. The next thing we are going to look at is something we call function mapping. And function mapping, it's very important. And the reason is that Python defined functions automatically apply themselves to each element in a Pandas data frame. However, user-defined functions do not do that. So we need to find a way of applying those functions to these data frames. And how to do that, we use something we call apply function and apply map. So we look at map, we look at apply first, and basically this one will do it row wise or column wise. So suppose we had a data frame that takes randomly generated values, normally distributed values. So we have our values, our data frame with columns B, D, E, and the columns for the 4 states. Now, if we wanted to get the mean the mean for the columns, then we can create something we call a lambda function that look like this. So we write the keyword lambda, and then we write x, and then x dot mean. So this one, it's like you're taking a single row x, and then you get the mean of that row. So basically we need to apply this function. Sorry, we have a column x that we want to get the mean for, or we want to get a mean for a certain, let's say a series x, and you want to get the mean for that series. So, and how do we apply that? We write our frame, our data frame, and then we use apply function, and we call our lambda function, which is f. If you execute that, so this is what you get. We get mean for each. So basically what happened is that the apply function did apply, actually literally applied the function f, which is getting the mean for any series. You pass it as an argument there. So it has been applied to other columns. Now suppose we wanted to use, instead of just having f, we can pass the axis you want to apply that to apply the lambda function to. So if we put axis 1, it's like you're getting the mean for the rows. But if we used 0, we would have gotten for columns. So axis 0, if you pass axis 0 there, we are getting the mean for the rows, for the columns. And if it's axis 1, we are getting the means for the rows. We can apply a different kind of, for several examples, we can apply a function that gets the maximum and minimum to the columns, and you can still do the same for the rows. In summary, there are those statistics that you can actually achieve. You can apply different. So as a summary, we can incorporate these in our lambda functions: count, mean, standard deviation, all this, describe, sum, whatever you want to do. So the next thing we can look at is apply map. Apply map will apply a certain function to each element in a data frame or a column or a row that you're interested with. Suppose we wanted to get a series of some statistics. Maybe, for example, we can have, we wanted to return minimum values in a certain series or a data frame, minimum and maximum. So we want to return the output as a map or a simple data frame. So here we want to get, for all the rows or columns, we want to get the minimum and maximum. So if we apply this, if we apply, we are getting the minimum and maximum for the columns. Now, suppose you wanted to use apply map, whereby you want to format the output, or you wanted to format the values of a frame in a certain way. For example, we can use these formats whereby everything will, all the values will have 2 decimal places. So basically it's like you're formatting all the values. So because every value will have to be changed, that's why we have to use apply map that works element wise. So to use apply map function, we say frame dot apply map, and then you pass your lambda function that does the formatting. So if I execute this, I see that all the values in our data frame, all these values have been rounded off to the nearest 2 decimal places. And that's basically what you get. And then the next thing we are going to look at is the most vital thing when dealing with data: how to handle missing data. So to handle missing data, we first call something we call NaN as NA. We're importing NaN from NumPy. So we say from NumPy, import NaN, and we can import pandas as PD. Now, suppose we had a series called data, and we are passing a list. We are creating that series with values 1 and A, which means symbolizes missing, and 3.5 NA, another missing, and 7. So if I execute this, I see that we have some 2 missing values. So how do we handle these missing values? The first thing we can do is simply just drop them. Drop the missing values just like that. If I execute this, I see that the missing values NANs have been dropped. Basically, drop NA function works the same as just selecting the non-missing values, just like this. So we are saying data dot not null. This will return either true or false. So anything that is true will be selected, and basically we get the same thing. But using drop NA function will simply just delete them from our data. So in a in a series, there are several ways you can detect the missing values or the missing data. And to detect, we're going to use an example. Suppose you have several states, 4 states, and then we also have a list of values, and one of them is missing, and we wanted to create a series from those two, the state being the index, and this being the data that we want as data. So we can create a series by passing as data and declaring that our indices would come from that list states. If I execute this, we get a list, a series whereby for California, NAN is missing. So how do we detect if we have missing values? Yes, here we can see, but assuming you had a million rows or a million elements, you can't possibly just have a look and see it. So we need to use a function called isNull to detect. So this function will just return true or false. And since we know that California is missing, then it's going to be true, but the rest would be false. We can also use another function called not null. So basically, we say PD, which means pandas dot not null, and then you pass our object 4 as an argument. So this will simply give you the same thing. It's gonna reverse, it's just like a reverse of is null. So is null checks if any of those are missing, and not null simply checks if any of those is not null. That's why we are getting false as the first for California, and the rest are true. So the next thing you're going to look at is how to fill the missing gaps or the missing values. And to do that, we use something we call fillna and pass different arguments. Now, suppose we had a series and we wanted to replace anything that is missing to be 0. So this is what we use. We say that's our data, and then fillna, you pass 0 as an argument. If you execute, we see that anything that was missing has been replaced with 0. Now, suppose you wanted to input specific values, we can pass a dictionary with keys representing with the key being the index that you want to replace, and the value being the value that you want to replace the missing with. So if I execute this, I get this. So which means that this was missing and has been replaced with 1, and also this was missing and has been replaced with -1. Also, we can do this. We can say underscore data dot fillna 0. We are replacing this. We are replacing the NAs here, because if you realize here, let me show you something. We've been doing some replacement, but have we actually changed our data set? No. we haven't changed. But if you wanted to change now in the actual data set, we use this underscore. Underscore is equals to data.fillna. And since we are saying in place is equal to true, then this will be replaced in the data set that has been saved in has been imported. And now trying to read the data, everything has been, there's no NAs because the NAs have been replaced in the actual data that we read or we created. Also, we can use various methods like just copying the values before or the values below. We can use the forward fill to replace those missing values. For example, forward fill means that the NA, the first NA in index 1 will be replaced with the values before, like this. You see it has been replaced with the value before. Also, we can do the backfill where we get the value, the next value, and replace the missing values. So here we are taking to replace this value. We of course took the value for index 2. So also we can replace missing values by getting the mean of the other values, non-missing values. So here we'll first get the mean for 1, 3.5, and 7, and whatever we get, we replace the NA, or we fill the NAs. So executing that, we see that we are replacing that with there and another one there. The next thing we are going to look at is how to fill the missing values in a data frame. And how to do that, we can have two data frames. I can print out F1 and DF2. Now suppose we combine those two. So we find that there are some missing values, E and row 3. So column E and row 3 are all missing. So suppose we wanted to replace the missing values with 0. This is how we would have done it. We say fill value equal to 0. So anything that was missing was, so basically we are getting this the sum, and anything that was missing would be replaced with 0. Therefore, we get the values, the sum of the non-missing values. So, and given that we do it element wise, we go and get A0, we add it to A0. So this is exactly why we are getting this. We have for column E, we're only getting the values from DF2, and the same happens for row index 3. We are getting the values for from DF2. Now, the next thing we are going to look at is filtering missing data. Under this, let's assume that we have a data set that takes the first row has numbers, the second row has only one number, and the rest are NAs, and the fourth row has one value missing. So if I execute this, I get 3 columns and 4 rows, and for row 2 has 2 missing values, row 3 has 3 missing values, and row 4 has 1. Now, there are various ways that we can clean up the data with respect to the missing values. We can use drop NA, and if I execute this, we see that we are dropping any row that has some missing values, which is not very good option. Also, we can do some filtering just the way we did here. We are just selecting values that are non-missing by simply dropping rows that have missing values. We can also do this. We can also specify how by saying how equal to all, and this will basically return the NaN only rows. And how to do that? If you execute, we see that drop NA is only dropping those rows with all the values missing. As you can see, we have one such row, row 3, has all the values missing. So that's why we are getting, by specifying how all, this will just drop all the rows with missing values entirely. You can also specify which axis to consider, and we still use our argument how equal to all, and we specify the axis. In this case, for axis 1, anything that is missing entirely will be dropped. So in this case, if I execute this, I get as entirely nothing has been dropped, since axis 1 is only considering the columns and none of the columns is missing entirely. But if we change this to 0, then it's going to consider the rows. If I execute this, you see the row that had missing values entirely has been dropped. We can also, that brings us to the end of this tutorial on Pandas. Please subscribe, like, and share my videos, and do leave a comment on how you found this tutorial. See you in the next video.